I'm a PhD student at the University of Newcastle, and I'm going to talk about a collaborative work with Olivier Jiménez, Julie Louvrier, Karine Prince, and Christophe Boitier. This is a tool for multiple datasets, data quality, and multiple years. So we're going first to talk about the type of data that we use in citizen science and the use of species distribution modeling. Then I will introduce our new dynamic framework and the ongoing model testing. And I will end by talking about some extension and limitation to this approach. So let's talk about citizen science. Anyone can make an observation and recording on an online database. We have the coordinates of a particular species sighting at a location. That's what we talk about presence-only data. But such type of data may be less rigorous than occupancy, presence-absence data, because they are coming from less rigorous plane surveys. But they are broadly used because they are very available online nowadays. And they are used especially in species distribution modeling. We use those coordinates observations combined with different environmental covariates, altitude, temperature, you name it, to predict where a species could be. But those predictions that we create are only as good as the observation we implement in our model. Unfortunately for us, in citizen science, the data quality can be very variable. And in terms of variability, we have bias in terms of noise, identification, and let's focus on this observation at the observer level for now. We have a recorder, an observer that have different age, experience, training, and a specialist observer may be able to do a better observation correctly for a species compared to a random observer, as we can see here. The identification of a species can also be of interest if you have species that are close to each other or difficult to identify. All of those create some kind of variability in the recording. Another point to make is about how do we make the observation? How do we sample the data? Because when you have your overall area, there might be this part, like the pink area on the bottom right corner, that could be difficult to access, a different type of vegetation. And thus, the coverage that you will have of the whole area may be biased and uneven. And that will be reflected in the pattern of points. Similarly, for the observers that go along the road that follow mainly a path, the pattern of point that we get will be uneven in terms of sampling effort and reflect the network of the road pattern. So how do we deal with that to more accurately predict species distribution? Well, many studies have tried to combine datasets to take the strength from different types of data in order to improve predictions. We can look into presence-only data because we have a lot of data, lots of information. And occupancy data is interesting because we have a planned survey with multiple visits. And that has been used in an approach by Ian Renner, Olivier Jiménez, and Julie Louvrier. And Ian will be talking about it later this week on Thursday. But they basically worked on a combined likelihood approach for presence-only and occupancy data, taking into account some bias, distance to the road, probability of detection, and using some lasso penalty for the regularization method. What I want to present to you today is some extension of this work, where we look into the observer recording, how the sampling is done, accounting for the variability in the different protocols, presence-only occupancy data, and also accounting for a dynamic aspect of this model, thinking that across years, we may have some extinction, colonization, some points coming up or disappearing from our area. So we're going to talk about that now. This new dynamic framework will combine point process model and occupancy data. Let's focus first on presence-only data. In a non-dynamic framework, we usually use Poisson point. We can use Poisson point process and model the intensity as a log likelihood function of different environmental covariates. And we can estimate the parameters of a model using a log likelihood function. Going dynamic, we decided to use a partial likelihood function, where every year contribute to the overall likelihood, and we model the intensity as different components. We have a baseline time component that is not much interest here and will be simplified in the model. We have a space component, and we have a stochastic part here that look into the dependence of the location on the history. So that's where our extinction colonization process can happen for this part. This approach is based on a Cox survival analysis and later developed by Deagle's work. And it's quite interesting because the partial likelihood is traceable compared to a full likelihood in the frequencies work here. What about the occupancy part of the model? In occupancy model, for a non-dynamic framework, we will usually model the detection and non-detection history to look at the occupancy states. And we can estimate the log likelihoods like we've done previously. When we go dynamic, here I will refer to some work done by Julie Louvrier and Olivier Jimenez, where they model the different states of occupancy. We have an initial latent state that refer to the environmental response process. We have a conditional state where we model the extinction and colonization that is happening on our occupancy. And then we can look into an observed state. So that's where we account for the probability of detection. And again, we can look at a log likelihood function for estimation across space, time, and number of visits. So what I want to summarize here is we used to see in this paper a model where we combine presence only, occupancy data. We account for lasso penalty for regularization. We have accounted for two types of data quality aspects, observer bias, detection for the occupancy data. What we improve here is we're going to account for observer score. So if we have different observers that we trust more in terms of if they were able to accurately make an observation, they will have a higher score. If we want to account for different protocols, we will implement some source weights. And we want to make that for multiple years. So we'll have also some extinction colony suppressions, like I explained before. And because we have multiple years, we implemented also a group lasso penalty in order to look into the link between the covariates coefficient in between years. And from this previous combined likelihood, we get this formulation with the weights and the group lasso penalty. But what do we get from this model? We are doing this ongoing model testing using simulation for starter. So we modeled some environmental covariates. Here we have 4 extinction covariates, colonization covariates, and 2 bias covariates for the distance to the road for presence only data, a probability of detection for the occupancy. Using the environmental covariates, we can get a species intensity and sample the points that will be our observations. This sampling is also biased because we biased it according to the distance to the road for presence only data and according to probability of detection for the occupancy data. This example have 2 years with 1 source presence only data and 1 source occupancy data. And I can input that in the model. What we get out of the model is different output, different information that will be explained also is in Jan's talk, but for my particular research here, I'm just going to present to you that we can have a coefficient shrinking path using the lasso penalty over 2 years. We can look at a certain model criterion, but I'm going to focus here on the coefficients because when I simulated my data, I have some defined coefficients that explain what the species is going to like. And my fitted model here from what we get is expressing a similar tendence from what I defined first. We added some dummy covariates where we can see that they are shrinked. So that's good because those variables didn't account really much in the model. What we can also look at is the intensities. We had some true intensities for the year 1, year 2. We see that the presence only and occupancy data show a similar pattern of intensity. We note a slightly different range of intensity here though. but also linked to the values of our coefficient that we got. But we can do more. We can add, like I said, source weight. If we trust more occupancy data in terms of information and accuracy, we can put a weight of 0.8, 0.9 for those data sets, and only 0.6 maybe for the presence-only data. We can also add observer score. For each presence-only data points, we can input some score that will rely on how we can trust the observer to make a good observation. All of that will be been testing and give similar results to what I showed you before with slight differences. But why do we want to use this model? Well, we want to use it if it's actually improving something, getting some better performances. So we've done some simulation to compare how our model in purple and pink will do compared to a simple presence-only data. This combined dynamic model is doing better than the dynamic presence-only data in terms of IMSC. We have lower performances, and better in terms of correlation, where the correlation is higher. But like I said, it's only simulation work for now. It's an ongoing work because we want to make sure that how we test the parameters, the initial condition that we're using, set up the boundary of a model and how it can be used. It's important here to test every aspect of our implementation: scores, weights, correction, bias, regularization method. So once we've all set up with that, we will apply it to real data sets. But the focus on my talk was on this statistical model that we want to apply for real data set issues. We want to take into account many data quality observations that are important in citizen science, observer bias, the behavior, using combined data sets, and allow for better prediction for management and ecological issue. Thank you for your attention.